As we introduce something brand new today, scientific notation, I'm going to have you jot down just this definition here, what scientific notation is. And again, if I go too fast, just hit pause, catch up, and then hit play again. But when we're talking about scientific notation, we're going to reference that as just a simple way to write a really big, a really small, and really big numbers. So huge numbers. You'll see things thrown around like Bill Gates's net worth. You'll see things thrown out like the amount of kilograms on the planet Earth that the planet Earth actually weighs, or really small numbers. We'll talk about like the mass of one cell or the mass of one atom inside of one cell. So things that are really big and things that are really small. Ways we can write those without having a ton of zeros and a ton of decimal points, or not even a ton of decimal points, but just like a lot of numbers after a decimal point. So ways we can be more convenient, more efficient, less pen strokes, and write those massive numbers. Let's dive in and find out how we can tackle that. So what I'm going to start with are three crucial components to scientific notation. I'm going to have you jot down each of these three. And so when we start, if you could just kind of make like a quick box with a decimal point in it, right in the center of it, a multiplication sign, another box, and then another box that's kind of raised to an exponent. The three boxes are going to be our three crucial components. Two of the boxes will constantly change. One box will stay the same. So first one that I'm just going to have you jot down. So I'd like you to label that first box number 1. And when we're talking about number 1 in our crucial components, when I'm just going to list these, and if you can put these in a list somewhere too, but we can at least connect them to the picture. Number 1 of the crucial component is a number between 1 and 10 with a decimal point. So we can write any number, gigantic numbers, crazy small numbers, but the first thing we need to have when we express that number is to convert that number between 1 and 10 and to put a decimal point. And actually, I should have said something more specific, but I think we can be precise with that language. Between 1 and 10, it can equal 1, but it cannot equal 10. It could be like 9.9, 9.99999, but it can't equal that number 10. So really you just need it to be in between 1 and 9.9 to infinity. But I'm going to keep that kind of written as between 1 and 10 because we can start with 1.0, but we're not going to write scientific notation with 2 digits like that with 10. We're always going to have 1 digit and then a decimal point and then something else, but we'll get into that as we continue to go. So crucial point number 1, expressing numbers between 1 and 10, usually with a decimal point. Crucial component number 2. And again, if you just keep building this list, that's wonderful too. I'm just going to have these different slides that talk about these things, but then I'll put them all together for so you can see them all together. Crucial component number 2, this is the thing that does not change, always constant when we write in scientific notation. Oops, change has an A in it. And that is this middle box. This middle box is always going to be the number 10. Always. So crucial component number 2 is that it's always 10. So the first box can change as long as we write that number between 1 and 10. The second box, and you'll notice this is after a multiplication sign, we're always going to multiply this first box by 10, some form of 10. So we're always going to keep the number 10 in this box here. So crucial component number 2, this box doesn't change. It's always number 10. Crucial component number 3 is this box up here. And crucial component number 3 is a exponent that we raise 10 to. So it's always going to be 10 to the power of something. And this exponent can be positive, as positive or negative. And it's really telling us how big or how small our original number is going to be. So exponent as positive or negative, and this is all going to tell us about decimal point movement. And this will all come together as we kind of throw some examples here. But earlier, I just wanted you to see these three components. We're going to have number 1 here, a decimal between 1 and 10. We're going to have number 2 there, always the number 10, and then number 3, an exponent written as positive or negative that's going to indicate to us decimal point movement. And we'll talk about conversions as we continue. But as long as you have those 3 crucial components, we are looking rock solid to start. For these next couple examples, I'm just going to have you listen to these, and then we'll kind of talk about some other examples about why this works. So for instance, if I start to look at a sample of scientific notation, I could look at 4.7 times 10 to the first. I have a decimal between 1 and 10. I have the number 10, and I have an exponent that's going to talk to me about decimal movement. So if I'm thinking about what this really means, I know that 10 to the first is equal to 10. So now if I say, okay, well, this is 4.7 times 10, and let's go with this again. Let me get some erasing going on here just to make sure I can keep my information squared, times 10. I know something about multiplying by tens, and multiplying by tens, it's really just adjusting that decimal point. And so I know that this is going to equal 47. For other examples, I know that 43 times 10 is 430. I know that 3001 times 10 is 30,010. So again, if I just look at this, it's just adjusting a decimal point. I went from 43 and I moved 1 space over to 430. I went from 3,000 to 1 decimal space over to 30,010. So it's all about just kind of sliding over a decimal point. We usually think about it as adding on zeros, but it's essentially just sliding over one more place value. We're going to go through a couple other examples thinking about this one, and I'll keep some things consistent. So now look at this example. I'm going to keep my same number here, 4.7 times 10, but this time to the second. I know that 10 to the second power is 100, and I know that is 10 times 10. So if we think about what I just said previously about decimal movement, I know that this is 4.7 times 10 times 10. And if I think about these, I know that 4.7 is just sliding a decimal point over to equal 47. And then I know it's doing the same thing here. So now if I'm thinking 47, and if I just want to slide a decimal point over, I'm going to get 470. And that's kind of what we talk about, that multiply by 10 rules, just adding on a 0. It's really just sliding a decimal point over. So we're going to look at one more example, then we're going to dive into something more complex. So here, if I now think about this, this is 4.7 times 10 to the third. I know that 10 to the third is 10 times 10 times 10, or 1,000. So if I think about it as 10 times 10 times 10, I know I'm taking 4.7 times 10 times 10 times 10. And when I look at it this way, I know that I'm just sliding decimal points. 47, 470, 4,700. And so now if I re-look at the shortcut, at really what I just did, 4.7 times 10 to the third, all I did was I just took that decimal point that was here, and I moved it over 1 spot, 2 spots, 3 spots, 1 spot, 2 spots, 3 spots, and I just wrote 4,700. So my crucial components give me where I'm starting, and I have this number 10, which stays consistent. It's all about decimal movement, and my exponent just tells me how to convert. So now scientific notation, I have this number 4,700. I can write it in this way. And to me, this yellow circle up here is harder than just writing 4,700. So let's look at something a little bit different that really gives us some information as to why scientific notation is super helpful. In lots of different scientific mathematical disciplines, we need to talk about massive numbers or crazy small numbers. You need to be able to calculate between them, understand them, get an idea of really what they're expressing. So what I have here, this is what the mass of the sun is listed as. And if I was needing to use this for any kind of information, calculations, this is an absurd number of zeros to write. Takes way too much time just to talk about different place values. This is where scientific notation comes in to help save some time. So the first thing that we needed was that crucial component number 1, a number between 1 and 10 to start our numbers. Well, I looked to see how I can start to look at this, and as I start to kind of factor and break this down into some different things, I know that if I start getting into here, I'm going to start looking at numbers between 1 and 10, or at least things that are non-zero. If I start to break my number there, I have 198.9, and I'm way over 10. If I break it here, 19.89, and I'm still over 10. That's why I'm going to start to look right there. And when I put that slash there, it's me just trying to start to write a number in between 1 and 10 using some decimal points to have some connection to this bigger number. So I'm just going to start there, and I'm going to write 1.989. And here's a connected number to our mass of the sun, but I wrote it in between the number 1 and 10. So I just kind of moved my decimal around. Usually what you're going to end up with is you're going to place it in between your first two non-zero digits. So when I say my first two, here are my first two non-zeros, but really we're starting to make sure that we just have one digit to the left, and then whatever else we have for non-zeros to the right, knowing that that's kind of how we write something between 1 and 10. So now I know that this number is always going to be 10 because it's all about decimal movement. It's all about massive multiplication. And so really what I'm going to try to convert is I'm really just asking myself, how do I take this number here in yellow, 1.989, and write it in a way that I can do this without writing all those zeros? Well, one way we can do that is kind of looking at multiplying it by these exponents of 10, or these massive factors of 10. So now what I actually have here is I need to figure out exactly how many spaces I can move my decimal. Because if I'm multiplying it by 10 to the first, I'm starting with my decimal point here, and I can just slide it over there. So that's 10 to the first, to the second, to the third, to the fourth, to the fifth, sixth, seventh, eighth, ninth, 10th, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28. I think I counted all that correctly. If I'm seeing that as I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29. I actually miscounted the first time, so I'm at 10 to the 29th. And so really now I could just express, okay, if somebody said, hey, we need to know the mass of the sun, this is the better way to say it, 1.989 times 10 to the 29th. And now I know this is a massively huge number. Another way, like we said, we can use scientific notation is writing crazy small numbers. So if we're ever needing to operate and kind of calculate with some things here, we don't need to write all the zeros out. We don't need to do anything there because we can have this idea of scientific notation. So if I was to ask you to convert this from standard form into scientific notation, you'd first start off with your second crucial component, knowing you're going to multiply something by 10. Then I'm going to look anywhere in here to get to my first two non-zero digits. So I'm going to start on the left and kind of keep scanning right. And I know that right there is going to be a nice number where I can be in between 1 and 10. If I go earlier, and if I put my decimal point there, I'm less than 1, 0.93. If I go and get over here and I put it there, I'm at 93.0, larger than 10. So that's when I need to place my decimal point right there, in between 9 and 3, to give me 9.3, something in between 1 and 10. Now, since this is a decimal, this is a crazy small number. I have a number that's larger than 1. Smaller than 10, but larger. This number right here is crazy smaller than 1. So what I need to do is I need to slide my decimal point not to the right this way, but to the left this way in order to equal this exact number. Because again, this is just going to be a major way that we rewrite this number without having all those different zeros. So if I'm going to look at that, I need to be shifting my decimal point to the left. I need to communicate that in my exponent up there. First, I need to know what number to put in order to get there. So if I'm starting here at 9.3 and envisioning that I have a decimal point there, I need to end my decimal here because this is the actual number that I have. So I'm just going to count decimal places between. If I'm kind of giving myself there between my two non-zeros, I need to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 spots to the left. So I went 10 to the 10th because I moved my decimal 10 spaces, but I moved my decimal point to the left in order to get to my in order to get to my actual number. So now if I gave you this information up here and I said, write this number out in normal form, you would say, okay, well, I'm starting here at 9.3 and I'm moving my decimal spot 10 spots to the left because it's negative 10. That's how you know you'll end up something there. So we know if we have a positive number in the exponent, we're going to have a massive number. If we're going to have a negative number in the exponent, we're going to have a crazy small number.